So in the previous lecture, I described the concept of the density matrix. It's a some sense more fundamental description of quantum mechanics than the vector space description, and I rewrote all the standard quantum axioms in the density matrix framework. Now that was all done using the language of what are called pure states, and it can be extended. So that is what I am going to describe today, the concept of what are called mixed states. Now, it can be defined very simply again by linear algebra construction, but this generalization has no description in the vector space framework. So it goes beyond, and you should keep that in mind, and that is why the density matrix language is more powerful. The linear algebra is kind of simple, that the all properties which I described last time, for example, normalization, expectation values, evolution, of the density matrix are linear in rho. Okay, that is the crucial point. I wrote down all these expressions last time, and linearity means that now I can add multiple of this density matrices and create a composite one which will all obey the same rules, because that is a generic structure of linear algebra. So if I define a new object which is a linear combination with some weights p, and I am going to choose these weights as probabilities, there is a reason for it. Then the same property will be satisfied by this new matrix rho m. This is actually taken for the simple reason that there was a one constraint, the normalization constraint, which was trace rho equal to 1, and if I construct this, then trace of rho m will also be equal to 1. This is all the weights, whatever I choose here, they add up to 1. Okay. Now, what is this object? Okay. It obeys the same dynamics, and there is a reason for choosing this. This is just an overall constraint for the normalization, but I am doing more than that. I am putting all these weights to be in the interval of 0 and 1 and calling them probabilities. That is another reason. I will come to that, but assuming that with if I now look at this object, some combination with some probabilities, then in the language of statistics, it's a statistical mixture. Sometimes the word which is also used is ensemble. It's a collection of objects with various probabilities assigned to various parts, and that is a statistical mixture because I am calling this as a probabilities. This is not the same as superposition. Superposition was also some combination like this, but it was at the level of the vector psi. So, you should not confuse the two. There are two different kind of objects. Why it is different? Because rho was a quadratic function on psi. I defined it as a outer product of the state. So if I do a linear combination of psi, I get superposition. But if I do a linear combination of rho, I get a statistical mixture. And these two objects are very different in their properties, and you should not confuse the two. Both of them exist in a different sense, but they describe also different phenomena. And in particular, the object which I wrote down as a result of measurement, where I last time gave the rule that density matrix after measurement changes to this new structure. What is this new structure? It is actually a statistical mixture. Because it was a probabilistic combination, with some probability I will get some particular eigenstate. And that is what this stuff is. This has no description as evolution of the state vector. It's what is called a projection. It's not a reversible step, it's an irreversible step, but this construction allows you to handle those irreversible steps also. So in particular, rho m can describe both it's a single object which can handle both these things. The evolution is the same as what was in the density matrix for a pure state because of the linearity, and it can do this as well because of this extra possibility of doing statistical mixture, and I don't have to invent two different axioms or description for dealing with them, they can be kind of merged into a single description. So that is actually one of the reason for going into this mixed state language, that different rules can be all put together in a single framework. Now, let me give the reason of why this pk are interpreted as probabilities, or rather that is the part which is useful, and that has to do with the concept of positivity. So, yeah, one more thing I can say, that when I do this combination, there is no restriction on rho k concerning orthogonality. It's not required for doing this. If you have an orthogonal basis, it can help, but even if they are not orthogonal, you can do a statistical mixture, no problem. What you generally need is a linear independence is good enough. And in many situations that possibility arises, they are not orthogonal, but still we can construct a mixture, no problem with that. What about the concept of positivity? And that is defined in different ways. One simple way of saying that is that all the eigenvalues of the matrix are positive. So in case of pure state, it was a kind of trivial statement because there were only two eigenvalues, 1 and 0, and because of this constraint on trace of rho, one of the eigenvalues are 1, all the others are 0, and you don't have to worry too much about the positivity. But now you are doing some linear combination. What are the eigenvalues of this rho m? Okay. And then it's a slightly different definition of positivity which is useful, which is saying that projection of this matrix along any direction is positive. What we are looking for is a eigenvector, but it is more general. If all the eigenvalues are positive, you take a linear combination of the eigenvector, the projection will still be positive, so they just add up. So how do I write the description for that? And that is now written as the combination. So which is nothing but an expectation value in the standard quantum language, and I treat this rho m as some operator. Okay. So if this projection is positive for all psi, then the eigenvalues of this matrix are obviously positive, because some of this psi can be chosen to be the eigenvectors, and then it will say that the projection along that direction gives me the eigenvalue which is positive. So this is in some sense more general definition, that instead of just asking at the eigenvectors, I will prove it for all vectors in the space. So now look at this object with this particular definition. So what happens if I insert for rho m this particular expression? I get the summation k pk psi rho k psi, and this was a pure state density matrix. So I know this object is positive. It will have some values, but basically dictated by the fact that eigenvalues of rho k are only 2. Possibilities, and so this number, whatever it is positive. So this stuff will be positive when this coefficient in front is positive. If there are negative values over here, there is no guarantee that this will remain positive. And that is the reason for putting these probabilities in this interval. And the consequence then is that rho m is also positive. So then the statistical interpretation is well justified. This new matrix is also a positive matrix. Its eigenvalues are not necessarily 0 and 1. It can be anything in between depending on what values pki stick in. But whatever they are all positive and they add up to 1. So that is a complete definition of the mixed state density matrix. Now, which geometrical structure it produces, we can describe that. So, if I put this coefficient between 0 and 1, and these are some objects which are pure state density matrix, I can geometrically look at this rho m as interpolation. This rho k will be the endpoints, and depending on these weights, it will be some value in the middle. Rho k are some sense the endpoints. They are the pure states, and these mixed states are in between somewhere. And those kind of features are very common in geometry, but here there is something more, that the space of this rho k forms what mathematically is called a convex set. You have to look at the whole topology to understand the meaning of convex, but I can just draw some arc, and just by drawing a line you can't say which side is convex and which side is concave. So the convention is, when you draw a curve, you look at it from bottom up, and if it appears convex, that like this, it is fine. If you look from top, it will look concave. So it's a convention, but you have to keep that in mind when you only have a partial description of what the space is, and then the interpolation will give something which is always above the curve, okay, for a convex set. This is more easily seen in the single qubit case. We had a complete description. It's a sphere, and sphere is a convex object no matter in which direction you look at. So then what is interpolation going to look like? That rho m will always belong to the interior of the sphere. So this is surface and now we can see that the space for rho m is actually much larger. This was only a two-dimensional surface. This is now a whole three-dimensional interior of a unit sphere. Because many more possibilities are allowed. And you can give various parameterization. What is a generic description of a point on the interior of the sphere? You can write it in language which I have used before. Where I had expressed the density matrix as identity part with coefficient half. That is just to get this trace equal to 1 and the Pauli basis. except that for the pure state, the coefficient for the Pauli matrices was a unit vector, the surface of the sphere. Here, it's a more general, any radius vector with magnitude less than 1. Yeah. You can write it in many different ways. This matrix is Hermitian, and that is why this Pauli decomposition is convenient. And this is one way to describe the number of possibilities, how they go up. If from unit vector, you allow any vector with a radius less than or equal to 1.
Yeah, but the summation of the unit vectors along with the probabilities, does that make no matter?
This had no probability. This was a pure state language.
The rho of m.
This one.
Yeah, so rho of m we write as like that, like a p of k with some.
Yeah, so I can write it as different ways. So that's one thing which I mentioned, that there was no restriction on rho k to be orthogonal. Okay, so that is why I took one point here, they are not necessarily orthogonal, and I get something in the middle. I am allowed to use that as well, that rho m can be described as many linear there is nothing unique about how I construct rho m. I can take linear combination of this, or I can take linear combination of that, or whatever it is, and actually many is infinitely many. Nothing restricts me for doing that. Some choice may turn out to be more convenient and I will use it, but in general, you can do such a kind of thing. And the reason it, when rho pure evolves to rho m, which means that you started on the surface of the sphere and went into somewhere interior. That interior could have started in many different places on the sphere, no idea what it is, and memory of the starting point is lost. If you are given only rho m, you cannot tell I came from this point or that point or that point. And that is the irreversibility feature which is buried in the concept of measurement. When you perform a measurement, you start from a vector psi, but then you do a projection. And that particular component remains. All the orthogonal components are lost. There is no way to recover them. And that is the same feature which shows up that yes, You found this mixture. How it came, no idea. And this is again a feature which is common with this statistical language. Many times in statistical physics, you talk about equilibrium. If you are given the equilibrium state, can you predict where it came from? No. That memory is lost. You could have reached the same equilibrium point from starting from here, starting from there, starting from there. Once you reach the equilibrium, that's fine. Memory of where it came from no longer exists. So this property is part of the description of rho m. So that is also something to keep in mind, that we generalized, but if you start talking about evolution, it can do this projective measurement kind of evolution as well, and then it can lose particular properties. There are different ways of expressing that as well. One notation which is used is if you take a square of the density matrix. In case of the surface, we saw that it was equal. Rho square was equal to rho. Here the radius, you can take a square of it, but because this r is less than 1, whatever you will get will be r square. So it will reduce in length. And one way of writing that result is describe this structure as rho square less than or equal to rho. These are matrices, so you have to understand what this less than sign it literally means. But this is follows from and this is m. Sometimes there is a different symbol because they are matrices. It's this kind of inequality sign which is also used. Some mathematically rigorous books will use that particular notations. That eigenvalues of these things are between 0 and 1 instead of being only 0 and 1. Only 0 and 1 will give equality. But if it is less than 1, then it will give this inequality. Yeah.
So, like you mentioned, like when we go from pure to the mixed state, so that kind of process we call it as Markov.
Yes. Markov doesn't have to be. Markovian evolution is much more specialized than the general situation which I am describing here. Markovian label is much more specialized. Okay, this is far more general than that. It's included here if you want, that Markovian evolution can be described in this language, but that doesn't mean that everything which is in this language is Markovian. There's one more thing I can say, that this kind of parameterization is all over the place, that rho k has in general 2n minus 2 real parameters that I described as a complex vector and then in n-dimensional space, and these two were taken out, one for normalization and one for the phase. Now this rho m has many more parameters. How many? Well, you can go back its definition that it's a Hermitian matrix, but the only constraint you have after that is the trace is equal to 1. There is no other constraint. You can do all kind of linear combination inside that. And you can see it in the case of the block sphere where n is equal to 2, and that gives a value of 4 minus 2 is the 2 parameters. Those 2 parameters were the 2 angles which define the unit vectors theta and phi, and I can get any point on the sphere by doing that. In this case, now n square minus 1 is 4 minus 1 equal to 3, and there are 3 parameters for the mixed vectors. You can write it as the 2 angles plus the length of the radius vector in the polar coordinates, or in other words, you can say that there are 3 Cartesian components of this which parameterize a general matrix. But that is a small difference in case of a qubit. The difference between this rapidly grows if you go to a higher dimensional space. There are lots of parameters which you can add to define a mixed state density matrix. Okay. So this is all the definition and interpretation of the mixed states. We will use it explicitly when dealing with open systems, basically a system interacting with environment, and that will come later in the course. Right now, I want to describe various consequences which are very simple, but we follow from all the axioms which I put together. And they all can be interpreted as conservation of information. And this follows from the fundamental evolution rule which we assume that a state can transform but by a unitary operator. Okay. So if you find the eigenvalues of a unitary operator, they have magnitude 1. Basically, it's a complex phase. This was one of the exercises in the assignment. And this simple fact says why we chose that in some particular way is to conserve something. The normalization of the state was preserved under the unitary operation, and that is why this magnitude was appears. So that is why you can call it that something remains unaffected under this particular evolution. So it cannot describe situation when the magnitude changes, and cannot describe processes like damping or decay if you restrict yourself to unitary evolution. Here are the processes where the magnitude reduces. Of course, we will have to address the question of how to include this, and that will involve the use of this mixed state structure in a very particular way. We saw how the magnitude reduced from going to n to r. Okay. But if you strictly stay with unitary operation, this cannot happen. And that means the states they keep on going round and round. If you look at the unitary evolution, if you have only eigenvalues of 1, what you can do is only go around in circles. It's not going to decay, and then it's not going to reach a fixed point. So the situation which I kind of mentioned, how do you reach equilibrium? It's outside this particular process, and you have to now see the restrictions which follow if you only stick to this unitary evolution description. Okay. So there are various other ways of writing it that the inverse operation exists. What is it? It's just a adjoint, which means I started at some point and went to another point in the space. I know how to come back. Okay, all this stuff about reaching an equilibrium and losing the memory is not part of it. And when you have this processes which are reversible, in physics there is a name for it, and that is called adiabatic processes. Adiabatic processes are actually a very particular case of a reversible processes, but there is a conservation law. And the variable which is conserved in reversible processes is entropy. The generic thermodynamics tells you that when you have an irreversible process, entropy increases monotonically. That is what we see most of the time in our real world. But if you go to a situation where the processes are reversible and you work out the value of the entropy, it will remain constant. That's the only way that you can go in the opposite direction. Because if you say that the entropy has increased, the inverse process will require entropy to decrease, and that is not allowed. So that is a important constraint, that the entropy is preserved. And the computer science label for it which I have mentioned before, that the computer scientists have a new name for it, they call entropy information. And so all this business tells you that for unitary operations, information is conserved. Physics says it is entropy, but it is a part of the game. And now this simple fact leads to various consequences, which are fairly straightforward, but worth understanding at the beginning, because those features are not there in our classical computers. The classical computers don't work in this particular limit. The entropy increases, that is why your computer heats up, it's producing heat. The consequence of this thing is that it can run without any consumption of energy. No heat. Heat, if it appears, will change the entropy. That is one of the relation in thermodynamics. So the process is, it's a drastic, and we will see examples. Explicit models. That in this particular limit, you can run your computer without consuming energy. It kind of drops out. Important component for the real computer systems, but in this idealized situation, well, you don't have to worry about energy for running the computer. All you are doing is you can call it a transformation or recycling. Nothing is created, nothing is lost. Only change from one description to another. That is all that happens under unitary processes. And this is a simple fact, but we are not accustomed to thinking about this in our classical description. So then what will the purpose of any of this transformation of recycling is that something in one description is not obvious. You go to another description, then the result becomes obvious. That's all you are trying to do. You are not creating something new, you are not destroying anything either. So now let me come to straightforward example. One of the often quoted result is no cloning. You can't make a copy because the process of copy is making 2 out of 1. It's a nonlinear process. These rules are not going to allow you to do it. This is again a linear transformation, whatever is buried inside this unitary language. So that means in the quantum scenario, there is no Xerox machine. So let us describe what we mean by copying. You have some state and a blank paper. When you copy it, you will have 2 versions of the same state. That's what you do in a Xerox machine. The original is still there and you have another one. And that is forbidden. Let's give a proof. Okay. Proof is kind of straightforward by contradiction, saying that this is allowed. Assume that you can give any state and there is a machine which will take you from here to here. Okay. So let us just 2 possibilities are enough. So some machine which gives you so this is a proof. It should be able to copy any state that the Xerox machine does. Any picture you give, it produces a copy of it. So assume that such a machine exists. So I have one state psi1 and another state psi2. Then I construct dot product of this with this, the inner product in more general, by taking the conjugate of this relation and multiplying with the other one. So what is the conjugate of the left hand side, which will give 0, let me take psi2 conjugated version, and this one the original version. U dagger U is identity, and whatever this 0 state, I will assume that it's normalized. So this is equal to just the inner product of psi 2 with psi 1. What is on the right hand side? What is the inner product? It will be two factors. And so there is some quantity here, the same quantity squared on the other side. These are numbers, inner products. Where is this possible? Well, it's possible only if this number is either 0 or 1. No other solution. If it is 1, then these two equations are not independent. It's the psi 2 and psi 1 are the same. I am not using a new state. So this is the same state. Or the states are orthogonal. And not for any general superposition combination in between. Doesn't work. And this one is trivial to say that this two copying whatever I did is not defining any new relation. The orthogonal ones are new, but they are in some sense, the set of basis states in the vector space. I can choose an orthogonal basis. And what we saw earlier while defining the Hilbert space structure, that the orthogonal basis states can be mapped to the classical description. And the full quantum state was any general superposition of this orthogonal state which defined the complete Hilbert space. The only orthogonal basis subset was the classical states. And so it tells you explicitly that the only possibility is you can copy it provided the states are orthogonal, which means they have a classical interpretation, which means that the classical Xerox machine is okay. The states, whatever they are independent and orthogonal, but in quantum superposition, no, not allowed. So
One question here.
yeah.
If psi 2 equal to psi 1, then it is possible copy pasting.
Well, that is not a general machine. No? It should be able to copy any state.
But
It can copy a specific state. I have no problem with that.
okay, that means at least one quantum state we can copy. but not true.
Yeah, so arbitrary general state defined by superposition cannot be copied. Specific states you can copy, no problem. And in terms of the kind of circuits which we'll draw at some stage to describe the computer, bifurcations not allowed. When you draw a picture like this in a circuit, you say there is a signal S, both of these points are supposed to have the signal S. That's forbidden. So in quantum logic circuits, you will never see a scenario like this. And it's a very fundamental consequence of all this unitary stuff. You can add more things. I cannot copy, but I can repeat the same argument. Can I erase? That is also not possible. All that is done is transformation, recycling. Erasure is also forbidden. Proof is almost identical, which basically is it's a simpler process. You don't even have so many factors. Something is there, I want to reset it to 0. That's the process of erasure. Can I do it? You can repeat exactly the same logic. So lat of assume two states, some operation which reduces both of them to 0. Then same inner product. On the left hand side I take inner product, u dagger and u will cancel out. And the right hand side will have one. Again the same trouble. It's even more restrictive. There is only one answer. That psi2 equal to psi1. I can erase a specific state, but not even two independent states. This creates all kind of questions, means some things which you are very much used to it. I am erasing things on the board. What is happening? Well, in the quantum language, I am not doing anything. I'm taking the chalk powder and it's now falling down somewhere over there. In principle, nothing is created, the lost, it is only recycled. And when you call it something erasure, you basically take something and put it in some place where nobody else is going to look. That's essentially the whole point. Nothing more than that occurs in a quantum logic. I can describe this decay process again in this language. It's very common. You see that the atom decays from the excited state to the ground state. You describe it very easily in quantum mechanics. What is happening is, well, the atom does decay, but in the process it emits a photon. And you assume that the photon ran away somewhere else, it is not going to come back. Then you can say that yes, it decayed and the photon is now lost forever. But suppose you put the atom in a cavity, that photon is not lost, it is still hanging around. Then it will come back and it can excite from the ground state to the excited state also. That will become a reversible process, provided nothing is lost. So whenever you talk about something getting lost, you are making some implicit assumption that some part of the system is taken out and put in some place where nobody is going to look. It's a fairly general description, but it is important to realize. And another feature when I'm talking about this circuits, you can write a description of a circuit which is almost essential, that at any point when you start a program, you say I'm making all the input register 0, which is this process. Then I run the program. There's something written in it, but I wipe it out and start. How am I going to wipe out? Because when I do the wiping out, I'm taking something and putting somewhere else, which is wasted in the usual computers as some kind of heat. But that is the process I have to rely on. Otherwise, I cannot initialize the computer to say everything is 0. And there is other feature which is related to this. There is the linearity. It forbids closed loops in the circuits. Which means there cannot be any feedback. That you did something, whatever came as a result, you take it back and put it in the initial state. That kind of a situation is also not possible. Because what you are assuming indirectly in feedback, that there is something in the output which I can use to modify the input in a particular manner. But what is happening in this unitary circuit, that the output is just a transformation of the input. You bring it back, it's not going to give you anything new. It is just like reversing the evolution from output to input, which is there. It's not going to give anything extra, which is assumed in the case of feedback. So there will not be any loops in the circuits. So the quantum circuits are very simple, just a bunch of lines. They go from the input to the output with some interactions in the middle. There are no bifurcations, there are no closed loops. In our electronic circuits, these things are all over the place, but they don't appear here.
A loop will appear to be addition of something, addition.
Yeah. And having described this, let me point out something else which is important to understand to avoid confusion. Okay. So, and this is again a very similar looking process, but it is allowed. And the distinction is important. If you want to take a general state, I wrote it down in some particular basis. And this is a blank paper. Can I perform a transformation which leads me to this kind of structure? The answer is yes. There is no problem at all. Or rather, this is a generic process which occurs in any evaluation of a function or even a straightforward thing like a measurement. What would you like to do in a measuring apparatus? That you have some state defined by some superposition of various coefficients, and you want the property of that state to be copied onto the instrument. That is what the instrument should show ultimately. And in that case, this is a system, this is the instrument, and that is what you want. And this particular transformation is not forbidden. Okay. It is, as a matter of fact, is a genuine unitary transformation which produces what is known as an entangled state. Two parts which are perfectly correlated in some sense. And how this is different than what I was writing here, that this is this thing is different than this equation in a very subtle sense. So I will write it down that what is the factorized version was in the same notation u acting on that is what this equation will translate to. There are two factors, one labeled by I, another labeled by J. And this is what we showed is forbidden. There is a double sum on the right hand side, while this one has a single sum. And there is no problem with this. It produces this correlated states are all over the place. As I said, when you try to measure, the first step actually will be exactly this particular evolution, and then the second step will be projection. So then you do a projection on this whole combination. These things are perfectly correlated. You will get the system to go into this eigenstate I. The apparatus will have the reading of that same I, with the probability which is mod Ci square. So this is a and it's going to happen in a much more general situation when you have interactions between two objects. It will produce this kind of correlated states. And it can be defined even more generally. You can perform a evolution of an arbitrary function by producing this kind of state. That there is a single sum, something which was blank, now is converted to some arbitrary function of this value of I. Here it was just left as identical, but you can change it. That's not a problem. And we will use this kind of a structure extensively because this is part of the algorithm. You have to evaluate various functions. How will you do it for arbitrary states? Well, you create this kind of correlation. The important point is that all this dynamics will involve entangled states. There are different parts of the circuits, but the variables are correlated in a very tightly constrained manner, and when you at the end perform a measurement, it will project onto that particular coefficient some state and some reading. until you perform the measurement, the unitary operation will only do this kind of a jugglery. And yeah, this is as much as I want to say about this information conservation, but yeah, there is another connection I can mention, that if you are given two states, psi 1 and psi 2, how do you differentiate between them? Okay. And in this generic language, it's not possible. I can detect psi 1 perfectly, but then I use the same apparatus to detect psi 2. Sometimes it will work, sometimes it won't, and when it works or won't work depends exactly on the same constraint. Either it is the same or it's orthogonal. If it is anything in between, then the same apparatus will sometimes give one projection, sometimes it gives other projection. So it's not possible to perfectly differentiate non-orthogonal states by any measurement. So and that is the same logic produces this, that you take any apparatus, you measure something, it will fix that particular basis, and then you can have that basis change so that the state you are measuring is an eigenstate, then it is fine. But if you now look at any other state, it can be either the same eigenstate or some mixture with some another eigenstate. And not mixture, superposition with some other eigenstate. And if it is orthogonal, fine, that another orthogonal combination you will call the second eigenstate, and you can redesign your apparatus. But if it is not an orthogonal state, then those two vectors cannot be simultaneous eigenvectors of the same apparatus, because the apparatus which you are using is a Hermitian operator, the eigenvectors are automatically orthogonal. So if it fits, fine, but if the orthogonality is not there, the measurement will turn probabilistic. One of them can be perfect, but the other one will not be perfect. So that is something which is part of the life when you are dealing with this scenario, but you can ask that, okay, I don't want perfection. What if it is just approximate? And then you can play a lot with that particular game. Yes, it is possible to make approximate copies. Make a copy, it's not identical, but yeah, it's something which is you can work with many times. Or you want to make a measurement, the measurement will not give you 100% probability, but well, you get some 90% probability, and you can maybe accept that. Then you need a criterion. How do you judge the goodness or the badness of that approximation? And these are mathematical formalism tells you what is the good criterion, and I can give the formula for it. It is called a fidelity. So, approximate copying or and fidelity is a number. You want something like a, what you call, so many percentage. It's a number between 0 and 1, essentially. And all this jugglery will tell you that what will be a good measure. Well, it is nothing but this overlap. It decides between the same thing and orthogonal. So, one definition is just modulus square of this overlap. Turns out to be a useful characterization, how good or bad that number is. And you can ask that can I design a machine which gives me fidelity of say 80%. It may be good enough for some practical purpose, but then you can ask that question in a more generality and not this unconditional statement that it should work for all the states. Work reasonably for some set of states, and that gives you the success probability. And this object is a convenient measure in the it's an overlap. Either you write a mod square of this complex number, or equivalently is the same thing as trace of the product of the two density matrices.
So 80% correct.
It will give you the right answer 80% of the time. That's what it means. That's what fidelity means. And this is a measure for it, whatever it is, where you can say one of them is the exact answer, the other one is approximate answer, what is the overlap. So I will stop at this stage today, but the point is that with very little extra work, the consequences of all these axioms can give powerful constraints, and they are buried in all the general discussion which will follow of what a quantum computer does, how it does, and what are the kind of results you can expect. I wanted to basically emphasize those simple points. I will give some more consequences again at the very simple mathematical level, which will follow from the same axioms before I go on to discussing the actual algorithms and circuits and what can be done for very specific problems.